How do light rays bend when they cross from one material into another? What is the index of refraction of water? These are the questions students will explore in Investigation 21A, Refraction of Light. Like a lifeguard trying to get to a swimmer, light travels at different speeds in different materials. The lifeguard will take the fastest route rather than a straight line, because they can run faster on sand than they can swim in water. When a light ray travels from one material into another, it takes the fastest path by traveling a shorter distance through material where its speed is slower. The index of refraction for light in a material is the ratio between the speed of light in empty space and the speed of light in that material. When we speak of the speed of light in a vacuum, we mean how fast light moves in empty space, not in the vacuum you use to clean your house. In Part 1, we will trace the path of light through air and water, measure the angles of incidence and refraction, and use these angles to determine the index of refraction of water. In Part 2, we will experiment with how different incident angles affect the refraction or bending of the light as it passes from air into water and back into air again. In Part 1, your students will look through a container of water at a line that's been drawn on paper, and then they'll measure the angles of incidence and refraction and use these measurements to find the index of refraction for water. In your kit, you will find a clear plastic container, and we will also use a protractor and a piece of graph paper. I have traced the outline of the container on my graph paper by setting it down, going around it. And I also drew an incident ray with an angle of 45 degrees from the normal. I filled my container with water and then put it back on the graph paper. Looking through the water, I lined up my straight edge with the incident ray. And you have to keep it straight and draw the line. And I drew the refracted ray. I emptied the container, replaced it on the graph paper, and then I aligned my straight edge with the incident ray, this time coming through the container of air. Match it up, draw the line. When I remove my container, I can connect the path of the light rays through the water and through the air. In looking at the incident and refracted rays that passed through our container full of first water and then air, we can see that light was bent by the water, but passed directly through the air. The light bent at two interfaces. First, when it passed from air into water, and second, when it passed from water into air. We can measure how much the light was bent by measuring our angles of incidence and refraction at each interface. First, I drew a normal, this dotted line, perpendicular to each boundary. Measuring from the normal, I recorded the angles of incidence and refraction in the data table. Using these angles, I used the Snell's law calculator in our online text to calculate the index of refraction for air to water and water to air. To find the index of refraction of water when light passes from air into water, I chose to solve for the index of refraction of the refracted medium. The index of refraction for air is defined as 1. The angle of incidence is 45 degrees. And the angle of refraction is 33. This gives us a value of 1.3 for the index of refraction of water, which is very close to the expected value. Checking for the refraction of water to air, we choose to solve for the index of refraction of the incident medium using an angle of incidence of 33 degrees and an angle of refraction of 45 degrees. We again calculate an index of refraction. We have to set the index of refraction for air. There we go. Now we calculate an index of refraction for water of 1.3. We expect the index of refraction for water to be the same whether light passes from air into water or water into air. Your angles may be slightly different than what I measured because we are eyeballing the path of the incident ray as it travels through the container, and we're also ignoring the small effect of light bending through the sides of our acrylic container. In part 2, your students will look through the container of water at incident rays with different angles. I used the container full of water, several colored pencils, a straight edge, and a piece of graph paper. I began by tracing the container of water and then drawing incident and refracted rays, the same as in part 1. I drew 3 more incident rays at angles that are smaller than 45 degrees, using different colors for each of the rays. One has an incident angle of 0. That is, it is normal to the surface of the water container. I put water in the container and looked at it through my incident rays, and then I drew the refracted rays with a straight edge. I removed the container, connected the path of each light ray, then I replaced the container, and I looked at the complete set of rays. We can see that the ray with the largest angle of incidence refracts the most, bending toward the normal so that it passes more quickly through the water. And the one that comes straight in, normal to the interface, is not refracted at all.